Uh, Hello everyone, my name is João Ricardo Lourenço. Let me check something. Is there anyone here who doesn't speak Portuguese? Okay, okay. So I'll talk in English. I'm going to talk about, I'm going to present my talk, what if you could predict exceptions? I'm going to talk about a new exception handling model, which was my master's thesis. Before I do that, just a little bit about myself. My name is João Ricardo Lourenço. I'm 23. I got my master's and my bachelor's from the University of Coimbra. In the last 4 years, I've done some research work at CISUC, mostly in the area of NoSQL databases and exception handling. I'm currently working at Scintillant, and I like just about everything about computers, except maybe front-end development, which I really hate. And other than that, I love security, distributed systems, low-level stuff. You name it, I really like it. Moving on. This is the outline of the presentation. I'm going to start with the motivation for this new exception handling model, which I will present, called Prax. Then I'm going to present the new model, a few preliminary experiments, a set of simulation experiments and why we needed them. Then I'll detail the implementation of this model, some final real-world experiments, and finally the conclusions. So I'll talk about 3 experiments, the model and its implementation. So, exceptions. We all know exceptions, we've all seen them, even if you don't use them a lot and just throw them away. They're present in most languages, either as a try except, try catch finally, and you even see them in some more exoteric languages. The idea of the exception and the try and catch, it's always there. And even if it's slightly different, these techniques related to exceptions, they always have the same underlying principle, which is an exception happens, which is an error, and then you react to it. And sometimes that's really just too late. It's kind of like hitting your car and saying, oh, well, now I have to fix it. And you say, well, it's obvious. Well, there's an error. I have to fix it. I broke my car. I have to fix it. But what if you didn't have to break your car? What if instead of letting the exception happen, you could see, oh, wait, maybe I'm going to crash. Maybe I'm going to stop this. Maybe I can predict this crash and stop it. And so I don't have to fix the car. I just have to break it. So the basic idea is to go from this scenario in which we have an exception and an exception handler with a set of recovery strategies that the programmer wrote in the catch block. You go to a different scenario where the exception can still happen, but now you can predict it. And if you predict it, there's an alarm, kind of like an exception, and you can write some code for that alarm. So the exception might still happen, but now you can try to act before it happens, before it potentially happens. And this gives you possibly new strategies and strategies that act before the exception. So say you're going to lose the connection to your database, you try to throttle down the rate of requests so you don't really time out and your clients don't really get kicked out of the server. And of course this is all very, very pretty. It's very pretty to say this, but it's easier said than done. And you need techniques in the area of online failure predictions to make the predictions. The area of online failure prediction has existed for a long time. It deals with predicting failures at runtime. That means while we're online. And it basically looks like this. You are at present time t. You have a data window with all kinds of samples about what you're doing, CPU samples, the number of miles you ran, you name it. And you're trying to make a prediction about the future. Is something going to fail? And you make that prediction with a certain lead time. And that prediction is valid for a prediction period. So you make a gamble based on the data. And online failure prediction has existed for a long time, but it's online failure prediction. It's not online exception prediction. It's not at the hands of the programmers, so usually you see this at the level of sysadmins. They see, oh, my program is going to crash. They have their sys logs, they have lots of logs. But our idea is that the programmer should be the one to be notified of this when writing code, because the programmer is the one that's notified of exceptions. So maybe he should be the one that's notified of possible exceptions. And so we decided, hey, let's build a new model where you no longer have a try catch, but you have a try, prevent, and catch. One for catching the exceptions and another one for the alarms, for the potential exceptions. So within the try block, it's all business as usual. Exceptions can be raised as usual, but an alarm can also be triggered. An alarm means, hey, this exception, it might happen. And if you receive an alarm, you'll jump into the prevent block, similar to an exception. But unlike exceptions, in the prevent block, you just want to run a bit of code and get back to what you were doing. So usually you get an exception and you terminate there. That doesn't really make sense here because nothing's really happened yet. But if you fail to prevent the exception with the code you run, or if it really is inevitable, you eventually go back to the catch block. So you have the try, prevent, catch, these 3 blocks, one for each of these situations. And you might notice there's also a little extra argument over there, which is called the prediction context. This is because when we're trying to predict an exception, you say, oh, I want to predict a null pointer exception. But I say, well, it can happen in a lot of circumstances. You can have that in a lot of places in your code. So it's really useful to know where exactly in the code that is. What's the context? What were you doing? And so you can specify a prediction context that bottles all the samples of data you use for prediction until there. So we have a couple of other features in our model. We have a sample keyword, which you can use in your code to give features for the prediction. So say you are writing a bunch of data to your database, it's probably useful for you to write the progress. So we can use that for prediction because we can use the rate of change of progress, for example, to detect if you're going too fast or too slow. So I think it seems pretty obvious that the more data you have, the more accurate your predictions can be. Doesn't mean they are, but it means they can potentially be better. We also have a keyword to disable alarms because you might not want to be jumping around in code all the time. So it kind of makes that sequence almost atomic. It isn't atomic, it's sequential. And we have a prediction information object which within the prevent block can give you information about the exception that's potentially going to happen, such as the lead time. It can tell you, oh, I predict this exception is going to happen in 10 seconds, 20 seconds, because you might want to use that for your prevention strategy. Who knows, you might figure out, hey, it's 3 seconds, I don't have time to do anything, I'll just write this to a log, something like that. So I've been talking about predicting exceptions, and it's probably a little bit fuzzy how this all works with the language. And this is the general architecture that we're proposing. Whenever you enter a try block, you have a code entity which talks to a coordinator. The coordinator is the big brain. It receives data from all kinds of probes. You can put a probe in your database machine, you could put a probe in your programs, you can put a probe everywhere, and it's continuously sending data that can be used for prediction. And it does machine learning. It grabs the data, it correlates it with information about exceptions, and it says, oh, this exception is going to happen in time X or time Y. So it looks like a single point of failure. It's because it is, but you can replicate it and all is fine. And these probes, you can make your own probes. The idea is that this is an open protocol, and you add that data, and automatically it will be used for prediction. And, well, of course, this all works very well, but you have to know how to make the predictions. It's not that easy. When we were working on this, we looked at online failure prediction, which has a lot of history on this. They have many methods. They have statistical models, statistical tests. They have function approximation techniques. But we realized there were two very important concepts for us. The first one is that we really believe that if you want to predict something, an exception, you need to take into account the time dimension. So you can't just say, oh, my CPU is 30% and my RAM is 50. You need to see the progress. My CPU was 30 and now it's 70, so I'm going too fast, I'm going to blow up. And we also wanted to make this model very general. So we don't want to have a priori knowledge. We don't have it to have to depend on a lot of things. We want this to be able to predict any kind of exceptions. So this excludes a lot of statistical models and tests which have assumptions about the data. And so we looked around at online failure prediction, what had been done, and we realized that the best way to go would be to use a machine learning approach based on classifier algorithms. Of course, that also means we need to know what to classify, because as I showed you, we have probes gathering data, and this data comes at random intervals. So you can imagine you're getting data at very spaced out intervals. And how do we convert that into an instance that we can then send to a classifier that says, okay, there's going to be an exception in X time or Y time. And we came up with well, we didn't come up with it, we adapted it, it already existed, with an algorithm that uses a sliding window. I'm going to try to show it to you. So consider that you have time, that's your arrow, time is moving, and the stars symbolize some data about CPU or CPU. So it means I'm measuring the percent of CPU usage, for example. And since the world isn't perfect, sometimes you get a lot of data, sometimes you get data really spaced out. And the little circles represent RAM. So two features that you can use for prediction. The first thing we do is we split time into windows of size t, those little lines over there. And after that, we say, okay, we have different windows. We want to make the data in them look the same because we need to have a classifier instance. And so we just summarize the features. So we have, for example, in the first window, we have three stars, 3 samples about CPU. We take the average, the mean, the average, the minimum, the maximum, the variance, the rate of change, and that's what we store. So each window has the minimum, maximum, etc. for each of these features. So it doesn't matter if you have 50 samples, you'll always end up with the same number of features in each window. And then we figured out, okay, so this doesn't really give us a lot of information about time. The only information about time here is the rate of change, which is the last sample minus the first dividing by time. So we decided maybe we can group these windows together, because that means if first we have the mean of the CPU, for example, you have the mean in the first window and the mean in the second window. They're ordered, so you see, oh, it was 50, now it's 70. If I see that pattern, that means something is going to happen. So we apply a sliding window, grouping these features, and this is what we send to the classifier. And additionally, we have a look ahead parameter. So you have this window, and you can try to predict for the next window or for 30 windows ahead, although it probably won't really work that well, but the model supports it. So that's all the theory. So the theory about how we thought about this model, why we thought we needed it. We really think it's useful. But this is what we thought, and so we thought this is risky. We want to make some preliminary exceptions to see, okay, is this really possible? Can you really predict exceptions? It sounds like a fairy tale. And the answers to this question was yes. We ran a little experiment using TPCW, which is an e-commerce benchmarking software. We stressed TPCW, it started blowing up with null pointer exceptions, and we said, hey, let's try to predict those using this technique. Not the full model, just try to predict. Gather data, try to predict. And we realized we could predict 91% of these exceptions with 0.12% false positive. So we were really happy, hey, we can really predict exceptions. Maybe not in every case, but in this case, so let's move forward and try to keep going with this. So let's keep going with this. So we thought, okay, the first thing was, can we predict exceptions? Now that we can predict exceptions, is that useful? So I mentioned that we have a prevent block in the code. We decided to see, hey, is it useful? Can we put something there that's useful? And so we decided to run a simulation experiment. Why a simulation? Well, because if we were going to run a real test, I wouldn't be here today, because we really wanted to adjust all the parameters. We wanted to simulate that we had a good prediction system or a bad prediction system. We wanted to see what would happen in all cases. and we wanted to vary the workload of our experiments, so we decided to implement a simulation. This simulation was similar to the preliminary experiments with TPCW. We tried to model it exactly. So this meant that we could also use the values for predictive capability. That 91% I mentioned, we were able to use it here to try and see, oh, if we had 91% ability of prediction, what would that mean? So we implemented this simulation, but the most important part of the simulation was, okay, so what do I do if I predict an exception, a simulated exception? And we started to think about it for a while, and we thought, hey, let's try something really simple. So the problem is, we had null pointer exceptions because lots of clients were connecting at the same time, and the database couldn't handle it. So what if we the clients come in and we see, oh, there's going to be an exception, so let's just sleep. Let's sleep for a while. Not a fixed amount, but a random amount. So say, we're going to sleep between 5 seconds and 10 seconds, or 3 seconds and 5 seconds, you name it. This had the very nice impact of, consider you have 30 clients connecting at the same time, they're all going to be distributed through an interval of time, so effectively the load will be lower, so we thought. And so we decided, hey, let's try the simulation experiment and let's just put a sleep there, simulate a sleep, which acts as a request throttler. And so these are our results of the simulation. There are only 3 lines that are really important here. The first one is the baseline. If you look at the x-axis, that's our workload, so bigger means more clients trying to do more things at the same time. And in the y-axis, what we have is the throughput. The higher, the better. So we see that up until about 150 clients, the baseline, so our model isn't used there, it's just the usual system. It is the best because it can handle everything perfectly. But as soon as it hits a certain threshold, it can't really handle the overload, and it starts having exceptions, and the throughput drops down very abruptly. On the other hand, if you look at many false positives, what that means is we are effectively, if there are many false positives, we are always predicting an exception. And you might think, oh, you're always predicting an exception, you're always entering the sleep mode, and you can see that because throughput is it's much lower in the beginning compared to the baseline model. It's the lowest line over here, but as opposed to that, it's the one that can handle more clients with the higher throughput. So it can go up to 300 clients. So the baseline couldn't handle any more clients at 300, but the many false positives could. And we also tried that data from our preliminary experiments, and we got the best curve in there. If you see, there's a very open curve in there, which basically means that you can handle a high number of clients and a low number of clients equally well. So we were very happy with this. It was just a simulation. The simulation is only as good as its model. But this gave us inspiration to go forward. Okay, this works. Let's just really implement this. This is a model we've been theorizing. Let's implement it. Let's see if this comes out as true in the end. And so we did. We had a lot of choices as to how do we implement this model. We originally thought maybe we're going to write something native. We were going to implement something at the level of the JVM. But we opted out against it because it was a master's thesis project and there really wasn't that much time. So we decided to implement this as a Java 8 library. What this meant was that it was easy to integrate in current projects, which was important for us to run some experiments. And I'm going to show you, it has a graphical look that's similar to the proposed model, so I'll show you in a while. Of course, this has some drawbacks. First, it's not exactly like the model. There's some handiwork you still have to do as a developer. You have to call a function sometimes, but it's not really that bad. And there's obviously more overhead, because having a library there, and you'll see with Lambda functions, lots of indirection, there might be an overhead. And there was, I'll talk about it later. So what did we do? What's Prax? The Prax system involves these 4 things. First, it's the coordinator, the big brain. You put it running somewhere. Then it's the library, which you import into your projects. So you can write the try, prevent, catch in your project and replace try, catch. Then it's an administration application, which is really ugly, and it's over there. And it allows you to, say, start training for some exceptions, clear data. It allows for some administrative tasks, which hopefully will be gone in further in future models, because it's really not that good to have that there. And then we built a probe which gathers data such as CPU, RAM, internet throughput, etc. And it sends it to our coordinator. And I mentioned that we managed to have a graphical look that is very similar to our model. On the left you see our model, you see try, prevent, catch, so that's just pseudocode. It's like the way we would like it to be in Java. And over at the right we have what we really have with our library implementation. You see that these are the main differences. We need to have a client there, we have a C dot there, we have a function call here. But overall, if you look at it, it really looks like the model we proposed. There's the try, there's the prevent, there's the catch, there's a lambda function going in there, but we were happy with this. It resembles the model we wanted, and it works as long as you call sync at the end. And as you see, there are lambda functions, so there's a lot of indirection going on here. But we implemented this. It took us a while, but we implemented it, and we said, okay, let's finally run some real-world experiments. And we wanted to answer these questions. Can we really predict exceptions with the full implementation? Can we help prevent them, because we had only simulated this? And is this useful, because we can prevent them, but if there are other techniques that do this better, then this really isn't that useful? And does this impact the performance of the system? Because if you can prevent exceptions, but the system goes down because it's really straining on it, it's not really that useful, is it? So, what were our experiments? We wanted to have some real-world experiments. We wanted to simulate a real scenario. So, we grabbed Shopizer, which is an open-source e-commerce Java application. People use it to make e-book stores, to sell their coffee mugs, or whatever. It's to make online stores. We modified it to include the Prax client, that little library. And we started overloading the server. So, we overload the server. Queries started taking too long until they timed out, and this eventually led to exceptions, similar to the previous example we had. And so these exceptions were the ones we wanted to predict and prevent. This is typical of Black Friday and of Christmas traffic, where you have normal traffic, and then suddenly there's an influx of clients, a very high workload, and everything goes down, it's the end of the world, and we wanted to try to prevent that. This is our experimental scenario. We had 4 machines. These 2 were sending lots of packages. We were trying to overload the system. Shopizer ran in a separate machine. It had a probe gathering the CPU and the data of the CPU data, RAM data, etc. And then there was the database. So maybe I didn't mention it clearly enough, but when I talk about predicting exceptions, you can use whatever data you want. You can use data from all the machines, from one machine, because the idea is that you are writing an application for your system, not for this machine. So you should use data available to you from all the system. And so there are a couple of things that are important about how we ran these tests. The first is that we had 3 different workloads, so 3 different kinds of spikes. The idea was to use all of this to train one model that was good for all these 3 workloads. So see if we didn't have overfitting. Then we wanted to compare our recovery strategy, which I'm going to tell you which one it is, with our preventive strategy, with a recovery strategy. So typically, when you have these connection timeouts, what you do is you try again, and you try again maybe a maximum of 3 times, and then you give up. So we decided, okay, let's try that and see what happens, see the throughput, and then let's apply our preventive strategy. Let's have the prevent block do something useful. And that something useful is the sleep I mentioned before. We said, hey, this worked in the simulation, let's see if it works here. If it doesn't, we'll go back to the drawing board. We didn't really have to go back to the drawing board. And finally, we thought, hey, let's see how this impacts performance. So let's have the Shopizer code with the modified try, prevent, catch running, but without exceptions being predicted. So it's only there adding noise. It's only there adding indirection in the Lambda function. So let's see if it performs worse than the original Shopweiser code without any modifications. And I'm going to show you the results. So this graph shows time. So we're running an experiment in one run, and there's a black line there. It's the start of our workload that will eventually lead to exceptions. It's when we start throwing lots of clients. It's Black Friday. Everybody's crazy. The green line is the throughput, and finally the blue line are the exceptions. So you clearly see that you start the workload, and eventually exceptions start happening. So okay, let's see what we can do. We ran this lots of times, we gathered data. The system does this for us. All we have to do is say train, it trains, and then automatically the prevent block can be entered. It's all almost magic. And so remember, the blue line exception. So this is without our system, base case. And this one is with our system. There's no more blue line. There's a little bit of blue line there, a little bit of blue line there. There are other colors, but that's not really relevant. That's for different. That means when you use the preventive, when you enter the prevent block or not. But the really big thing here is we were able to predict and prevent these exceptions. And if you compare the throughput, it's very, very similar. We are able to reduce the number of exceptions in each run on average from 200 to 3, 200 to 3 again, and from 132 to 1.2. So we managed to reduce the number of exceptions by these factors, 54, 68, and 10, all by doing a sleep. So imagine if we did something different, something more sophisticated. And we even saw a slight performance increase in the two workloads, though they were within standard deviations, so that they're very similar. So this was great for us. We were really happy. Now let's see if it has an impact on the performance of the system as a whole. We tried that. We disabled the prevent block, so we just ran it. We just let it run with a bit of overhead from having the library. And indeed, the library adds a bit of performance, but it's not that significant. And we realize that this impact is there because you no longer have a try catch. You have try, prevent, catch. You have Lambda functions in there. They get passed around. That's overhead that is due to our implementation. But in a native implementation, it's not really going to be there. And so in conclusion, when we started this project, we had an ambitious goal. We wanted to try and make you think that, okay, right now you have exceptions, you react to them, but maybe you can do something different. Maybe you don't have to react to exceptions, maybe you can prevent them. Maybe you can let your programmers write the prevention code, maybe they can do something wonderful with it, maybe they won't do something wonderful with it. And we wanted to see, does this offer advantages? And to us, it showed that it offered advantages. When we compared it with the traditional strategy, we were able to reduce exceptions, to increase the throughput marginally. And so this was only the first implementation of this model. We designed the model, we implemented it. It can be easily introduced in existing projects. We had to do it in Shopweiser. It was very easy. And so even if you don't really like this concept, if you think it's not useful to you, this try, prevent, catch concept, I'd like you to really think about it in your own personal projects and say, maybe I can try to think outside of the box here. Maybe there's something I'm reacting to. Maybe I can predict something here. Maybe I can try to act differently here. Because we take a lot of things for granted. I never thought, when this project was proposed to me, I never thought, oh, I'm going to act before an exception happens. That doesn't really make sense, but it did, and maybe there can be some kind of breakthrough in your area with this. And that's it. So thank you. If you have any questions about what was done, go ahead. Thank you.
Hello.
Hello.
Congratulations for your work. It's very interesting.
Thank you.
And I would like to know if you have played with the idea of adding intelligence to the probes so that the coordinator could not only predict the exceptions but also take corrective measures itself.
I'm sorry, could you say the last part? I didn't really understand the last part of the question.
I would like to know if you played the idea with adding intelligence to the probes, right? so that the coordinator could not only predict the exceptions, but also take corrective measures itself?
Well, currently the catch block is still there, and so right now we predict exceptions, and you as a programmer, you get thrown into the prevent block, and you can do whatever you want there. You can see, oh, I'm going to crash, so maybe I should just clean up the memory. Maybe I should inspect and see, oh, this client's doing a bit of naughty things. Let's throw him away. So you can already do that because one of our main ideas was usually sysadmins deal with this tricky part of errors and exceptions and faults, and we wanted to leave it out of the hands of the sysadmins because they didn't develop the applications. You're the one developing the application. You're the one that might know why things are failing, and exactly you might try to have some corrective measure. If you think about it, all of the actions you have in the catch block, such as starting new connections, allocating more resources, you can still have them in the prevent block, except they're being done preventively. So to answer your question, yes, you can already do that in the current system, in the prevent block. Well, if we're all done, I think that's it. Thank you.